Welcome to this session on geospatial analytics. It's a bit of a weird situation because I'm also the session chair, but I'm also the speaker, so I have to introduce myself now. I promise to keep it short. My name is Skerlak. My background is physics, mostly quantum physics and atmospheric dynamics, a bit different. And now I've been working at Migros, also analyzing data, but slightly different data. So I've been a data scientist at Migros for 4 years now. And today I'm going to be talking about revenue forecasting or the store location planning process in general. So it really boils down to the question of, should we build a store here? This is a situation right outside here, if you guys know it. It's a beautiful building, does not belong to Migros yet, unfortunately. And it is really all about, should we try to get a space in this building? Should we try to open a supermarket? So for today's talk, Migros really is the Migros supermarket. I know Migros Group is really big. There's lots of enterprises in the Migros Group, but I'm really referring to the classical core business Migros retail. So when you look at such a situation, there's so many local influences, right? Like a planner could go and say, oh, there's so many people walking around here, I'm sure they're going to buy their groceries in this store, or there's good public transport, or there's this nice conference setting nearby, and there's lots of things that are not really captured by data. Parts of it is, and part of it is not, or also if there's projects planned, or maybe it's a really good offer for this building, or maybe Coop has a store back here and you just really want to be closer to the roundabout just because you can, not even to make a profit. So there's tons of reasons why you would want to or not want to build a store. So the decision is very, very complex and is also very, very local. So as data scientists, we cannot really answer all these aspects with data, but what we can do is we can provide a sort of standardized or a tool that enables the local planners to come to a good decision. And by us, I mean the Federation of Migros Cooperatives. So a quick recap of the most important boundaries within Switzerland. These are the 10 Migros cooperatives. So 10-second story of Migros. Migros belongs to roughly 2 million households in Switzerland. These are the foundation of Migros, so to say, and they're organized in 10 regional cooperatives. So you see the boundaries here. From a geospatial point of view, it's of course perfect. They don't match any other boundaries, so not even Postleitzahl. So of course you have just own polygons for that. And so if you were to plan a store outside here, this would be in the domain of Migros Aare. So they would be in charge of the decision what kind of store and how big it's. So these 10 cooperatives, they operate the Federation of Migros Cooperatives, or in German the Migros Genossenschaftsbund, which is located in this tower building in Zurich, so at Limmatplatz, if you ever wondered what this tower is for. This is where we're headed. Our unit, Data Strategy and Science, is taking care of the data strategy for the whole Migros Group, but also really solves very concrete use cases. One of which is this assisting local planners in making good decisions. So our goal, data-driven, is to provide an accurate and interpretable forecast for the revenue of a new or an existing store. And an important aspect is also we have to be able to do that for arbitrary scenarios. And by arbitrary scenarios, I mean situations where, okay, we know this Coop over there they're rebuilding next year, they're going to grow. Then there's a new Aldi coming to that street, and we might close this other small Migros that's not really performing well. So we have really a complex scenario, and we could also think of, well, there's a new building being built there, lots of apartments, or there'll be new customers over there, and store planning is a process that is aiming at time scales of years or even decades. So you have to ramp up the store. It takes months to years until you reach your full potential, and people have to get used to that. Oh, there's a new store in town. So we want to model all these scenarios, and in the end, we don't want to have an email API, quick link to Swissly, but we want really an appealing graphical user interface. So we want to have something that's easy for the user to use. And of course, you guys know it, geospatially, anything on a map is already really cool, right? So our tool is also based on a map. powered by our collaborators at ESLI. And I do not have the time to show you the demo here, but I do have my laptop, and we have a stand outside, stand number 14, right by the stairs. And I'm very happy to show you guys, let you also play around with the tool, plan your own little store in your neighborhood. And if you get the right numbers, I can forward it to the respective cooperative, and you can plan the store of your dreams today. So the tool looks kind of like this. It's, of course, a map. I'm not going to say what the color is, but we have all the stores nearby, and you can then click and add new stores, move them around, modify them, then press a big calculate button, and it puts out all the numbers that you need for your plan. Okay. Now, when you think of, okay, how would you do such a calculation? So the most important number is you want to have the revenue that this store will generate. And if you think of that, it's really a classical regression problem, right? You can approach this, you can approach this by trying to model your target function, so to say, is the revenue. How many of these are you going to make a year? And the input depends a lot on your store location, of course. So your store has some other Migros maybe nearby. It has some other Denner nearby. Maybe a little small, tiny Tante Emma Ladele, Quartierladele kiosk. There's other competitors in the vicinity. It really depends whether you are on the countryside somewhere or you're in the city. How many people work in the neighborhood, how many people live there, those are customers. And also, of course, if it's next to a big train station and your store is open on weekends or late at night, that has a drastic influence, of course, on your revenue potential as well. And this guy here is our famous Einkaufstourismus. So near the border, people have the tendency to go buy certain goods in Germany, and then some people from Germany buy other goods in Switzerland, and you kind of have to take this effect into account as well. Of course, also France, Italy, and so you could think of creating lots of features for your stores, and then try to model the revenue as a classical supervised learning algorithm. The way you approximate this function, I will rate in the terms of this thing as accuracy. And this is the 1 over interpretability, so it's like confusion, how confusing it gets or how hard it is to explain the results. And the first simplest one, of course, is linear regression. Might not be that accurate, but it's very good, very well interpretable. The next one that's used a lot is tree-based models, so be it boosted trees or random forest or just classical cart. They tend to be a bit more accurate, but a bit harder to interpret. And then on the other extreme would be deep neural nets, where you might get very accurate results, but it's really hard to explain the results in the end. And now, this sort of order might be true for some other problems. We found for our problems this is not really true, but think of this as we don't really have big data in this context. We have big data in other contexts at Migros, but not so much in the store planning, because there's only about 5,000 supermarkets in Switzerland, so you don't have millions and 100 millions of training data. We only really know the revenue of our stores, right? We cannot, I mean, if we're open for data in that respect, so please reach out. Someone for a goal or so. Yeah, so our training set is not that huge, and what actually is, when we compare these algorithms, is more like this. So they're more roughly the same in terms of accuracy. You can get a little bit of epsilon here and there, but that's not really changing the order of magnitude. And so because we really like interpretability, we base our model mostly on linear regression. I'm expecting some boos now. So that is we tried the other stuff. It's fun to try, but it really didn't perform that well for our situation. I'm going to explain why. Or also, like, generally for all these machine learning approaches, one big problem we faced is there's some very basic common sense situations that are very hard to capture or not even solvable with machine learning. It's maybe a bit strong to say can't solve it, but I would argue it's very hard for it to solve this. So imagine you have a situation where there's 4 households, 1 Migros, 1 Coop. Everybody spends 100 francs on food, and because the Migros is closer and nicer anyway, 300 of this goes to Migros, and then there's 100 to Coop, okay? So you have 400 francs in total, and your model might capture this. Now imagine the new situation, there's a new Denner moving in because people like to buy alcohol as well. And then there's an Aldi and a Lidl nearby. And now you run your machine learning model on this situation. And you will get revenue for this, and for this store. But most likely, the revenue you get is not going to sum up to these 400. You're most likely going to get a little bit less here because you somehow modeled the interaction that there's competitors here. Also, you then are okay a bit more alcohol and tobacco, and you will get some less revenue over there. But this total sum is much more than the 400 you had before, and now you have to explain that to your planning expert. Okay, my model outputs these numbers, and he's going to go, well, are these people all being promoted at the same time, or what's happening over there? Where does this money come from? And that's really a big challenge that not even your best neural net can solve with 1,000 training points, I would argue. So to convert this into colorful signals, accuracy, yes, you might reach good accuracy. Interpretability, depends on what algorithm you choose. And arbitrary scenarios, I would argue red. No, this is not really possible. If you haven't seen the situation in your training data set, you're probably not going to get a well-interpretable result at the end. So the second kind of model we use is very close to what we saw for the cats and dogs in the previous talk. It's a gravity model, it's a heuristic model where we try to model the consumer decision where to spend their money. So imagine the situation, this is again where the people live, they want to go shopping. It's a small Migros here, a big Migros here, and a Coop over here. And now we try to model these blue arrows. These are the probabilities that they're going to go do their shopping here. Or what percentage of their shopping are they going to do in these respective stores. And the gravity model is called gravity model because it's roughly related to the law of gravity in physics. And so the gravity of the attraction of a store, how much it pulls your money essentially, is typically modeled by its size or attractivity. And this attractivity can be a complex function of, say, size, format, your assortment, opening hours, whatever. In the most basic one that's often published in literature, it's just the size of the store. The bigger the size, the more attractive it is. You know, it's not true these days when you just want to go quickly inside and want to quickly leave again. You don't really want to go through three stores. So this is an assumption you have. The more attractive, the more it pulls. And also, you know that really well, if the store is far away, it's less attractive. So it's really size or attractivity pulls the money, and distance inhibits you from going there, essentially. And we try to then again calibrate this model and optimize the parameters for households, but also sometimes you don't start your shopping mission from home, but you say you work somewhere in the vicinity and then you want to do your shopping on the way home. So it's really important also to model the influence of people working there, say office buildings, large construction sites and things like that. So also these are modeled using a gravity model, and thirdly, also the same for train stations. So we have commuter numbers, and then we try to model where they spend, in which stores do they spend the money. Now this kind of model is very good at solving this problem. Because the total amount of money before was 400 francs, and the gravity model, by adding these new stores, you just shift the probabilities, but they still sum up to 1. So the sources of money, so to say, the 400 francs, the total amount is still the same. It will just be redistributed according to these changed probabilities. So with a gravity model, like with this heuristic approach, you can model any scenario really, and it will give you a more or less reasonable output. It will make sure you still have the same total amount of money, and it's easy interpretable. These guys get less because they're further away in the most simple part. But you can, of course, tweak that and make it much more complicated. So in the end, I would argue, well, accuracy a bit less maybe than the machine learning approach, but very easily interpretable, and you can model arbitrary scenarios. And of course, we bring this together and create the project manager's dream of everything has a green light. And we combine the machine learning and the heuristic model together, and everything looks amazing. It's accurate, interpretable, arbitrary scenarios. I would argue, with a little bit of a caveat, it is interpretable if you merge these two together, but it takes a bit more understanding. So the pure gravity model is easily interpretable, and this one is a bit more tricky, but we put a lot of effort into making it as interpretable as this one over here. Yeah, that's the summary of it. So how does this look now? We have implemented this solution it's been operational for a bit more than a year now, and it's being used probably currently as well. So it's really in production, so it's a data science product in production, and I want to show you some data and logical layers of how this system is constructed. So the base of our model is the data from the Federal Office for Statistics, the BFS. These are the two data sets we also heard at the Geo Summit a lot yesterday. It's the household data, the Stadtpop. So for every hectare, these are 100 by 100 square meters. We know how many people live there, how many households, what age the people are in this hectare. And we have the same for the working population, broken up down to industries. You can have how many people work in restaurants here, how many people work in finance over here. So this data set is publicly available from the Federal Office of Statistics, and it's a very detailed data set. So this is the foundation of our analysis. And on top of that, we take the commuter numbers from SBB. We also learned yesterday at the Geo Summit that SBB has a very good open data portal. Unfortunately, they don't have the commuter numbers there, but they have them in another data source where we estimate, so we can compare, say, Bahnhof Winterthur versus Bahnhof Bern. Like, how do they compare? How do we model the influence of revenue near these train stations? And then, of course, we have some in-house data. Thanks to our great loyalty card Cumulus, we have somewhat of an idea where people that buy goods at this store, where do they live, where do they come from. So we have some information on the geographical distribution of the revenue streams. So we can sort of also, again, calibrate our model and give it a little bit of a reality check. The last one then is, because we don't have that for our competitors and they don't provide a nice API yet, we have to get the data ourselves. We'll crawl it from the web. I'm sure they do the same for us. It's a bit stupid. We could just exchange the data because it's just inaccurate and a pain, right? I mean, yeah. But yeah, that's the way it is. Political issues. So this is our foundation of the data, and then we feed that into this gravity model, which makes sure we have a reasonable output. And that's easy and interpretable. But what we do then is we use the machine learning component on top of that to make the results more accurate, essentially. So this then tweaks the numbers around. And because then the numbers are tweaked around and say conservation of money is not satisfied anymore, we got to tweak them back down. And I call this layer business logic or magic sauce or name it as you like. But there's a lot of effort to make these results after the machine learning layer easily interpretable again, so that people, the planning experts, can really justify their decisions. They say, okay, these people, this revenue comes from this neighborhood, and this store is going to lose that much if we build another store here, and so forth. Then one slide for the techies. This is how our system is built. It's all based in the browser, so Esri has developed the user interface. People log in with their browser, they can save projects and store everything. So they can add stores here, they can change our stores, but other stores as well. They have views on hectare and postcode layers. Again, happy to show you that outside the poster, stand number 14. This connects to our single source of truth. Our database is a Teradata database, and that in turn is connected to the whole jungle of at least 1 million other Migros systems. So this will be the Migros data jungle, and fortunately enough, we have a nice guy in IT who takes care of this part, so a data engineer who creates a nice view on all these systems, because it's maybe not so clear, but I mean, Denner is also part of a Migros, but to get the Denner, just the store locations and sizes, for instance, was a bit of a mission already, and then you have the same for Migrolino, Voi, Migros Partner, and so forth. So all these things are nicely pre-processed into this database, such that we can consume it from there. So the user clicks together all the scenarios, and that is then sent via a REST API to our analysis server. We do everything with CI/CD with GitLab, and we use Nginx as a reverse proxy. And I'm very happy to share more details, maybe offline afterwards as well. So then to end up, what are some lessons learned? Well, Agile, I'm not saying like proper Scrum or anything proper Agile, but very intuitive process was crucial for the development and the success of this project, because Migros, really 10 Migros, you have 10 regional kings, and they all have their wishes and their dreams and their attitudes towards technology, legacy software. Some really like the previous tools, some really hate it, some really want accuracy, other ones want this, and we try to manage all these demands and squeeze them together in the common denominator. So we had to, we go to the cooperatives a lot, and we talk to them, what do you want, what do you need, and that was really crucial. And we also learned that while accuracy is really important, it's even more important for the results to be understandable, and also for it to be able to model any new scenario that you could think of. And then yes, of course, this business logic layer, the last one, was really crucial. Even if your machine learning produces more accurate results, you really have to do some tricks to make it really easily understandable again. So I managed to stay in time, that's good. And I'm very happy to take some questions. Thank you.